In Unit 4 waves, we're going to start off by looking at 4.1 oscillations, and we'll need to just sort of describe what an oscillation is to begin with. It's a term that you're probably familiar with, but we'll just sort of define it a little bit more clearly. So an oscillation is basically just a back and forth movement, so anything that's sort of moving backwards and forwards and in a regular rhythm. So it's happening not just sort of in a sort of something swaying in the breeze where it kind of will bounce backwards and forwards irregularly. We're talking about things that moving with some sort of regular rhythm about them. When that movement occurs in equal time periods, we give that a particular name as well. And that term that we'll use here, it's a little bit of a strange one, and not one that you necessarily need to memorize. It's just a term that the textbook uses, and so one that I'll just mention here just so you're aware of what that means. We'd call it an isochronous oscillation. So the idea there, iso basically meaning the same or consistent, and chronos relating to time. So examples of that we'll refer to, and we'll actually sort of set up some of these in class and measure them and have a look at the graphs that we can produce. The first one is a pendulum. So something like a pendulum on a grandfather clock. And the other one that we'll deal with that you might sort of think, well, it seems a bit strange to use this as an example, but it's actually a fairly useful idea for a number of different devices. It would be a mass on a spring. So they're the two scenarios that we're going to have a look at in more detail in class, but just to sort of describe them here, imagine we've got a point here with where a piece of string would hang naturally with a mass on the end of it, but we pull that mass out to the side. So we've got this pendulum, and so that mass there, when we release it, would start to swing back through this position here and then start to swing back up over to the other side. So at some later point in time, that object is going to be positioned over here. Now we know from experience that if we release that from that position, it's going to swing over this way, then it's going to turn around and start to come back this way again, and it's going to turn around, it's going to keep doing that sort of motion. An oscillation. Now in this scenario, the restoring force is always going to be acting back towards that position in the middle there, so that we can indicate that as the force. And the reason that force comes about, just to put a brief explanation behind it, it's the unbalanced force between the weight of the object that's acting in a vertical direction downwards, and then the tension in the string that's acting in sort of along the string, and so the vertical components cancel out, and we're left just with that horizontal component of the tension that provides the restoring force, causing the object to move back to that central position. Now the other one that we need to look at is a mass on spring oscillator. So imagine this is some fixed point from which we're hanging a spring, and the spring looks something like this with the mass underneath it. Now if we were to extend that spring further, so I'm going to draw this diagram again, but represent the spring having been extended, so you can see here that these coils on the spring are a little bit longer. That means that the object has now had a force applied to it to pull it down, and so there's a restoring force that's going to be acting back up towards that position at rest in the middle. If we then were to release the mass from this situation on the right, it would then start to move back up towards that middle position. So if we consider this position across here, and then it would continue to move past that, and so we then also need to draw the fact that that the spring is going to be just a little bit more compressed than it was initially, and the mass will then be a bit higher than that original position. So in that situation, the restoring force is actually going to be acting in a downwards direction here. So the motion of this object is basically that it's going to keep oscillating, so down to there and then back up again, and then from there it's going to go up and then come back down. So we get that repeated motion. Now if we have a look at the motion of either of these situations, if we consider the displacement of the object, so that would be that vector there, so that's x, or if we can likewise consider what's happening over here, it would be the position down to that location, or equally up to that position. Graphing the position, and we're using the vector x here, so the position, otherwise known as the displacement of the object, over time t. What we would see is a graph that looks something like this. We will actually have a look at this in class, and we'll set up a mass on spring oscillator, and we'll try it with a pendulum as well. So we get this oscillating motion backwards and forwards, where time is on the horizontal axis, and on the vertical axis we have the position, or the displacement, x. So we'll look at that in more detail in class, just setting up, like I said, a mass on spring oscillator and a pendulum to get a bit of a sense as to how this motion occurs, and then we'll start to quantify some of those values that can be varied about this particular motion.